Let's look at an example of finding the cross product of two vectors, x and y, where x is 1, 3, 4, and y is 2, 7, negative 5. Remember, the entire idea is to produce a vector which we call x cross y. The cross is not a vector, it's a symbol. This is x cross y that is orthogonal to x and y. So the whole picture that we're looking at geometrically, if you have two vectors in R3, perhaps you call this vector x, and then vector y comes down, I don't know, this way. So this is vector y. And those are in R3, so they're in a plane in the actual board, right? So here, these two things are kind of in the same plane. We're going to test the limits of my capacity to draw here. So these are in the same plane in R3. Then the whole idea of the cross product is it's going to produce some third vector. And let's see here. I actually drew this incorrectly. The way that I'll fix this is just to switch these, right, x comma y, and then the cross product is going to be x cross y, and this would be orthogonal to both x and y. The reason I knew this, I drew this incorrectly, is if I do this one pointed in this direction, this one pointed in y, the cross product should be the one pointing upward by the right-hand rule. Method 1 to solve this, use the component form of the cross product. Use formula for component form. And this is where I would use your brain, not your notes. Every time I did this for the first n times, where n is bigger than 1,000, I would actually think through what the heck I'm doing with relationship to the area of a parallelogram, because one of the key insights that's really helpful for creating a logical structure to remember this was to think that the cross product itself just has three areas of parallelograms. All right, so remember that in the first component, we were going to delete the x, and we're left with y, and we said that j cross k was a positive I. So this was something like y, I guess I'll use the thicker marker, y1 z2 minus y2 z1, and that was in the positive I direction. Okay, and then we said that the second component of the cross product came from canceling out the second component and then taking the area of the parallelogram that results, but we also said that I cross k, the first cross the third, when I do I cross k, I got a negative j, so we had to swap them, right? Instead of the x1 coming first, the x2 would come first. So this was x2 times z1 minus x1 times z2. The negative we've already factored in here, so we just leave this as j, because if we factored it in on that one. And then the third component came from canceling out the z's, and we already said that I cross j was positive k. So here we had the area of the parallelogram in the third one was x1 y2 minus x2 y1, and this was in the positive k. Way back when I was a young man without gray hairs and with a lot more hair on my head, I used to sometimes draw this with a little hat. I actually like the vector symbol a lot better because it reminds me of vectors. Sometimes you'll see me revert back into those old habits. Okay, now we can literally just substitute the values in. So y1 was 3, z2 was negative 5, and then we had y2 was 7, so we subtract 7. z1 was 4, Okay, so that's the first component of this vector. We'll go ahead and look at the second component, which starts with x2 as 2, and we multiply that by z1, which is 4, and we subtract away from that x1, which is 1, and z2, which is negative 5. And then the third component of this sucker comes from this equation, which is x1 times y2 minus x2, which is 2, times y1, which is 3. Okay, so this is the end of this bracket. And then the rest of this is stuff that hopefully we can do in our mind. So this is minus 15 minus 28. Here we have 8. Minus a minus becomes a positive, so 8 plus 5. And then, of course, this is 7 minus 6. And here we have the hardest problem we've solved so far. Minus 15 minus 28. That looks like it's going to be 43 to me. 8 plus 5, we're praying that that's 13. And 7 minus 6 is 1. So our claim now is that in this particular example, using the component form of the cross product, I have this. For those of you who are at home, I want you to know I didn't look at the formula for the cross product once. This formula has 6 different things that I have to remember, and I generated it in my mind. And I would encourage you to practice like that. Of course, on a test, you wouldn't want to do this. You'd have this on a formula sheet or something. To speed things up, but I think it's really useful not to have to rely on some arbitrary formula that you don't necessarily understand where it comes from, but instead encode it in your mind. Okay, so this was method 1, which was to generate the cross product using the component form. Method 2, we're going to see this determinant trick for the cross product. So we're going to talk about method 2. So let's go ahead and solve this using a second method, which is called the determinant technique. And the determinant technique is kind of fun. It says that if you want to produce the cross product x cross y, this cross product actually comes from the determinant of a very special 3x3 matrix. Determinants, I love determinants. They're not my favorite linear algebra topic, but they are actually quite interesting from the standpoint of some of the things that allow you to do in numerical analysis, which is kind of fun. So here in the determinant, you're going to write I, j, k at the top, and then you'd write the vector x right down in the second row of this matrix, and the vector y in the third row of this matrix. Anytime you see this is a 3x3 matrix, by the way. So this is a 3x3 matrix. And all this means is that there are 1, 2, 3 rows. So this is 3 rows. Rows always come first. And then this is 3 columns. Again, the first row is the row I, j, k, and they're vectors. The second row is x, and the third row is y. Here we see that these straight bars are determinant of. So you're taking the determinant of the inside. The determinant actually comes from, if we analyze some of the why we do the determinant. You'd see this in a linear algebra class. I'm not going to do it here. There's a beautiful definition in terms of permutations. I have these elsewhere on my YouTube channel. I don't want to truck with that. I also really don't want to truck with the cofactor method. Some folks like it. There's some recent linear algebra research that had an interesting result having to do with the cofactor method. I despise it. I just think it's ridiculous. Because there's so many better ways to do this. So I'm going to teach you this little trick, which is to append on the outside the first 2 columns again. So here we're going to write I, 1, 2. That was the first column. Here we have J, 3, 7. That's the second column. And then what we're going to do is draw diagonals and put positive scaling factors along the downward diagonals. And this actually comes from the sign of permutations. There is an actual deep mathematical reason that has nothing to do with this diagram. This diagram just happens to be kind of lucky. But there's a really cool math behind what's going on with this. For now, you can just think about this as a cheap encoding. Cheap in the sense that the only reason we do this is that you're literally trying to get the answer out of it. Okay, so now what we're going to do is multiply these out. So I times 3 times negative 5, this is going to be negative 15i. And we put a positive associated with that product. And then we've got j times 4 times 2, which is 8j. And then finally we've got 1 times 7 times k, which is 7k. Those are all positive. Now we're going to go on the upward direction and do the products along the diagonals, but associate a negative with that. So here we've got 2 times 3 times k is 6 with a negative out front. So this is minus 6k. Here we've got 4 times 7 times I, which is 28, but it's a minus 28i. And then again, we've got negative 5 times 1 times j, which is negative 5 times a negative is a positive. And I hope you notice something quite powerful. This is minus 43i plus 13j plus k, which if we write in component form as a vector is minus 43, 13, and 1. And we claimed that this was x cross y, right? Do you notice something about the connection between the solution that we got previously using the component form and the solution that we got using this trick? They're identical. Pretty cool, right? So that's the determinate technique using, how to take a cross product using the determinant. Just kind of a cheap trick. Next, let's see how to be even more efficient by using Mathematica to take cross products. And I hope your jaw drops when you see this. All right, let's switch over to Mathematica. Here we are in our Mathematica screen. Let's go ahead and find the cross product of the two vectors that we were studying in our previous example. X was equal to 1, 3, 4. And then y, in this case, I'm going to put a semicolon. That suppresses the output. I'll show you what that means in a second. So y was equal to 2, 7, negative 5, I believe. I should confirm that those are the examples. Yeah, that's for sure. When I put a semicolon and then I evaluate, I've been evaluating cells by clicking evaluate cells. I actually never do that except in these videos. What I do is I hold shift and I push enter. And another way to do this is just put on a Mac anyways, to push the enter on the numeric keypad. Do you see when I delete the semicolon, Mathematica actually prints output? But when I have the semicolon there, it doesn't print it. So in this case, I'm saying please set x, the variable x, equal to this vector, which is stored as a list in Mathematica. The moment I put a semicolon, it says do not print the output. So this little OUT 10 means it's the 10th output evaluated by the kernel in this run. So when I put a semicolon next to each of them and then I evaluate, here I go, shift, hold shift and hit enter. Now what we're going to see is if I type in x and evaluate, x is stored in memory in the computer, but it didn't print it unless I asked for it. All right, I promised you a really quick way to calculate the cross product between these, and to do so I'm going to put cross of x and y. Do you see that? No hard work done. Mathematica, meaning to say we don't have to do crazy calculations. Mathematica automatically produces that cross product as long as I call it correctly. So here I stored x as a list, which was the vector that we said. Y was a list, and then I produced the cross immediately. I wanted to show you another thing. Mathematica also has this thing called dot, and the dot product gives you the dot between x and y. So if I took the dot product here between x and y, I'd get 3, and you can confirm that at home. And why I wanted to show you this, let's call it equal to n. So we're going to store the cross product between x and y as a new vector n. We made a claim earlier in the videos for lesson 4 that the cross product should be orthogonal to both x and y, which means when I take the dot, remember, what does it mean for a vector to be orthogonal? It means when I dot x with n, I should get 0. Let's try dotting y with n. Yep. The normal vector n is orthogonal to both x and y, which is what we claimed by construction. This is what you can do with software. You can test things really quickly that might, by hand, take you 5 or 10 minutes, and you might even make a mistake. So beautiful. I want angels to sing. All right. In the next video, we'll start talking about algebraic properties. See you there.